solar-powered UAV BS for 5G and beyond. Greatly Bello and then Michael Mayo. Politicano di Torino, Italy. Abstract. Unmanned aerial vehicles equipped with a base station, UAV-BS, are considered an effective solution to dynamically provide additional capacity in radio access network RAN in case of network congestion or emergency situations. To face the problem of the poor energy availability provided by onboard batteries, UAV-BS can be equipped with photovoltaic PV panels to investigate and understand the complex interworking between traffic need and energy availability. In this paper, we propose a model of PV panel-powered long-term evolution LTE multi-user multiple input multiple output MU-MIMO UAV-BS using discrete representation of energy in terms of energy package EPs. The model highlights the different operation regions under which the traffic demand can be satisfied for given energy production levels. Results for winter and summer seasons that take into account daily traffic and energy production variability are shown and can be used to properly dimension the UAV-BS power supply system in terms of UAV-BS, PV panels, queuing systems, in energy package, introduction, mounting base station, BS on unmanned aerial vehicles, UAV have been proposed as a promising solution to dynamically deploy fast and flexible communication facilities where traditional ground infrastructure are not feasible or cost-effective. Through the additional capacity provided by the UAV-BS connectivity is brought to the users that are suffering from low quality of service. UAV-BS adapt their aerial position where needed, based on the position and the traffic requirement of users who are connected to the UAV-BS through access link, while UAV-BS are connected to the core network CN, establishing backcore BH link between them and the access point AP in 5G and beyond 5G systems. The access networks supported by UAV-BS have been considered for cases of terrestrial network failures due to network overload or physical unavailability, like festivals, concerts, sports matches, and natural disasters. As introduced in 3, in 6G networks, UAV wireless networks, also known as UAV-assisted networks, or drone cells, besides being employed to provide additional radio coverage, will be also used as content providers and computing servers in order to meet the growth traffic demand, which is expected to reach 1 zettabyte per month in 2028 and might saturate the 5G capacity within 2013-34. The new role of the UAV in the lands is possible because of the advance of their structure, which makes most recent drones able to carry up heavy payload. Up to some years ago, no more than 600 gram payload could be brought, while the most recent drones can transport up to 8 kg, much more than the 2 kg weight needed to bring access and BH networks equipped. Nevertheless, an important challenge that needs to be addressed is related to the secrets onboard energy availability that is provided UAV-BS by onboard batteries. This is an issue which actually characterizes UAV in general, but when they are used as communication infrastructure, the situation worsens. Indeed, besides the energy need for the flight of the UAV, also communication unit has to be powered to provide the service, resulting in higher energy consumption and reduction of the UAV-BS drive time. To cope with this, solar-powered UAV-BS have been proposed, which result in longer UAV-BS server without adding significant mass to the device. 6-7. While solution is promising, several issues need to be tackled. In 8 to 10, the optimal UAVBS location is optimized, revealing that a higher UAVBS altitude increases the PV panel production while negatively affecting the quality of service. QoS the survey in 2 highlights that the solar panel dimensioning and the understanding of the effect of intermittent energy production on the communication service provided by UAVBS network is usually neglected in the literature. In this paper, we studied the dimensioning of the PV power supply system of the LTE, MU, MIMO UAVBS by investigating the interplay between traffic demand and energy generation. To avoid that the energy consumption of the communication unit negatively affects the lifetime of the UAV, we assume that the amount of needed energy is provided by the PV panel, while the power of the UAVBS flight is taken from the battery. Without loss of generality, we consider these two energy consuming entities as independent, and we leave the effect of their possible power exchange as future work. We model the communication unit supply as a queuing system. We using a discretized representation of data and energy flows as data package DP and energy package EPs. As in 11 to 12, the transmission of the DP is triggered by the arrival of EPs when an EP reaches the system, but no DPs are available or the system is already processing a DP. That EP is unused, and if enough battery capacity is available, moved to the battery and employed to the power UAVBS flight. Through the Q stability conditions, we investigate the battery production levels that are needed to satisfy the traffic demand, the probability that an EP is delivered, and the trade-off between the system stability and the energy losses is discussed. Finally, the time variation of the produced energy and traffic demand is considered to make the system more realistic and to derive the proper dimension of the PV panel which should be installed on the UAV. Related work to exploit the potential of the UAVBS networks. Our key challenges to address is sacrifice onboard energy availability 13 to 15. Indeed, typically UAVBS are powered by onboard batteries, which limit the survival of these drones. To overcome this, solar-powered UAVBS have been proposed in literature. In many studies, they are equipped with PV panels to produce electricity without adding significant mass or size. 2. Authors in 6 prototype solar-powered drones, which can fly for 28 hours, while in 8. Senator maximize the system throughput of UAVBS networks powered by PV panels, which are installed on each drone. Besides this, the usage of the solar energy for the network infrastructure supply and for the BS of LAN in particular has been receiving a lot of attention for many years, since its usage allows to make the networks more self-sustainable, energy efficient, reducing also the electricity bill. 16. Also, the modeling community focused on the dynamics of the renewable energy harvesting in communication systems to derive its formal representation, which is fundamental for its proper design, dimensioning, and the qualifications of the effect of changes of each component to satisfy the needed requirement. These works typically use a discretized representation of data flow, digitalized in DPs, as well as the energy in terms of EPs, which correspond to the amount of energy which is needed to process a DP. Authors in 17 provide the Markov model of a BS totally powered by renewable energy sources. The model consists of a 3Q system. The first acts as an energy storage storage. The second is the data queue, and the third is used as a reserve energy queue. The analytical model for a generic energy harvesting transmitter equipped with an energy battery, where incoming EPs are stored, is presented in 18, which formulates the outage and overflow probabilities due to lack of energy and throughput. System description. The considered scenario is depicted in Figure 1. The UABBS provides additional capacity to users who access the CN using the access links between users and the UABBS and the BH links, which are established between the UAB and the APs. As in 19, we consider a femtocell BS equipped with multiple antennas using the multi-user, multiple input, multiple output, MU-MIMO. The access networks uses 2.6 GHz LTE femtocells based on technology, whose links budget is set as 20, according to which radio coverage is 830 meters in line of sight. The BH links works on the 3.5 GHz frequency and a bandwidth of 20 MHz, consisting of 100 resource blocks, RBs 20 to 23. The UABBS is equipped with PV panels that harvesting energy from solar and convert it to electric energy. The PV panels is used to supply the transmitting unit of the drones, while the battery is used to make the drones fly. In this works, we focus on the PV panels which produce energy for data transmission. The MU-MIMO femtocells BS is modeled as queuing systems with M servers, as depicted in Figure 2, where which servers represent a single MIMO antenna. Data and energy flows are discretized in DPs and EPs, respectively, and the waiting in line in which the DPs are waiting to be transmitted is assumed to be infinite. To transmit a DP, servers need an EP. This means that as soon as the server ends the transmission of DPs, it switches to sleep mode until the EP arrives. When this occurs, if there is at least DPs in the DP waiting line and the available server, the server is activated and a new transmission starts. In case there is no DPs to be transmitted, that EP considered lost and cannot be used for transmission of DP. An EP that reaches the system while all the servers are busy sending DPs is lost as well. As already mentioned in illustrated Figure 2, actually the lost EPs are not wasted, but moved to stored in the energy battery. If enough capacity is available and employed to supply the UABBS mobility, as in 24/25, DP and EPs arrives at the system according to Poisson processes with rate lambda and beta respectively. The DP transmission time has exponential distribution with parameter mu. Model description and analysis. Analysis of single server DP queue. We started by analyzing the LTE-BS equipped with a single MIMO antenna. This is modeled as a single server queuing system, as reported in Figure 2 as described before. When the server completes a service, it switches to sleep mode until an EP arrives. When an EP arrives, if there is DP in the data queue, a new transmission starts. The system is equivalent to the one drawn in Figure 3. When the server finishes a DP transmission, it enters into a vacation time, during which it is inactive and waiting for an EP arrival. This is modeled as a sleeping box, represented in green in Figure 3, acting as a delayer before the server can start transmitting the next DP in the queue. If any, the time spent in the sleeping box is exponentially distributed with parameter beta, and we called it sleeping time. Once this time expires, i.e. an EP arrives, the server is reactivated, and if there is DP in the waiting line, the actual transmission starts. See blue part in Figure 3. and rest for the transmission time. The service time is defined as the time dp spends in the orange rectangle figure 3. It is given by the sum of the sleeping time, that is the time waiting for the EPs, and the transmission time. In our case, this is given by the sum of two exponential random variables with parameters beta and mu respectively. The system can then be modeled as an MG1Q, where the probability density function of the service time G, as discussed in 26, is FGX beta minus mu x minus e beta x. The mean value of service time EG and the variance VAR GR respectively. Beta per 1 plus mu per 1 and beta square mu square plus beta square plus mu square. The MG1Q is stable if lambda EG per 1, that is lambda. Hence the system is stable of probability that an EP is lost. The probability that an EP is lost, LEP, can be written as LEP equal LEP empty plus LEP BG, where LEP empty is probability that an EP is lost because when it arrives, no DP are present in the system. The server remains in sleep mode and no transmission starts. It is given by the probability and to find the queuing system empty. LEP empty 1 minus lambda EG. LEP BG is probability that a EP discarded since when it reaches the system, the server is active and transmitting a DP. LEP BG lambda EG 1 per mu per 1 plus beta per 1 mu per 1 equal mu per lambda, which is probability that the queue is not empty, lambda multiplied by the probability that the server is processing instead of sleeping. Out of stability condition, which means that 1 is not satisfied, LEP empty is 0. Since the DPQ diverges and there are always DP waiting to be transmitted. Similarly, since there is always some DPs waiting in the queue, transmission times alternate with times waiting on EP to arrive, and an EP is lost if it arrives during a transmission time. The probability that an EP is lost is LEP BG equal mu per 1 plus beta per 1 mu per 1 equal mu plus beta per beta. B. Analysis of DPQ with multiple servers. We now discuss the LTE-BS equipped with multiple MIMO antennas. Using mu MIMO, this is modeled as a multiple server system, each server representing a single MIMO antenna. The system can be modeled as the bidimensional continuous time Markov chain CTMC x equals xt, in which the state is given by s per dp, where d is the number of dp in the system, both waiting and being transmitted, and p is the number of servers that are transmitting dp, i.e. the number of transmitting MIMO antennas. Transmissions are reported in table 1. Arrivals occur with the rate lambda and increased by the one number of DPs in the system, D. A departure of the DP occurs with the rate P mu, where mu is the server rate and P is the number of servers that are transmitting DP. Finally, a transmission starts if there are available servers P and some DPs that are waiting DP and an EP arrivals with rate beta. To study the ergodicity of the system, let us focus on the service capacity of the system with M servers, or the maximum service rate that the system can reach. The maximum service rate is reached when the load is high and there are always DPs to transmit. To investigate this situation, we introduced a new model that we call maximum service rate model. The model is MMQ in which service represents DP's transmission, and the customers represent the EPs that enables a service to start. As soon as the EP arrives, a transmission can start if some service is available. Since the EP cannot be stored, the capacity of the waiting line is 0. The probability to lose an EP in these conditions is denoted LEP-BG and is the M servers are already busy. The probability is the loss probability of the MMMQ, the very well-known beta formula, EB and beta per mu. The throughput of the service capacity model, which represents the maximum service rate of the DPQ with the multiple servers is equal to SM beta 1 minus LEP BG. Hence, the DPQ with the multiple servers is stable and the CTMC acts organic and reaches a steady state distribution if the DP arrival rate is smaller than maximum service rate, i.e. if the following conditions hold: lambda beta 1 minus LEP BG. From the solution of the CTMC acts under the ergodicity condition, it is possible to derive performance indicators when the system is stable. Let pi dp be steady state probability to have a DDP in the system and p servers that are processing DPs. We can derive the probability that an EP is lost because it finds no DP that needs to be processed. LEP empty sigma p equals 0 and minus 1 pi pp. And the probability that an EP is lost because when it arrives at the system, all the servers are already busy processing DPs. LEP busy sigma dm pi dm. Loss probability. In this section, the models previously discussed are verified by simulation experiment. We simulate our scenarios with M1, 2, 3, 4 servers, beta and mu equal to 0.5 and 1.0 respectively, and lambda varying between 1.0 and 0.89 with granularly 0.01. We measure the EP loss probability, which is probability to lose an EP. Remind that lost EP are actually not wasted, but moved to the battery and used to the supply of the UAV-BS flight. Figure 4 reports the total probability of losing EP LEP on the left. The probability to lose an EP because there are no DPs to serve. LEP empty in the middle, and the probability to lose it because the servers are busy. LEP busy on the right. Loss probabilities are shown versus lambda and the cases with M1, 2, 3, 4 servers plotted respectively in blue, orange, green, and red. Vertical lines show the ergodicity condition on the lambda as in 6, while horizontal dashes lines in the plot on the left indicate LEP-BG as in 4. Observe the two different regions which correspond to the Q being stable or not that differ for the behavior of the loss probabilities. For low values of lambda, the DPQ is stable. As lambda grows, the probability to lose an EP because it finds the Q empty, LEP empty decreases, while it becomes the more and more likely that the EP finds the servers busy. LEP busy grows interestingly when the system is stable. LEP assumes the same values independently on the number of servers. When the number of servers grows, the probability to lose EP because the servers are all busy smaller but this is compensated by probability to lose an EP because the Q is empty. When the Q becomes unstable, i.e. when lambda exceeds the condition in 6, the probability LEP empty is 0, while the probability LEP busy is given in LEP busy as in 4. Let us now on the ergodicity conditions. While increasing the number of servers from 1 to 2 has an important beneficial effect on the maximum service rate. Any additional servers produce only marginal improvement, which tend to vanish. Indeed, by increasing the number of servers, the probability LEP-BG reaches 0, but the maximum service rate is 5 converges to the EP arrival rate beta. Hence, we can conclude that by increasing the number of servers, it is possible to increase the number of service rate, less tight ergodicity condition, but no benefit are achieved in terms of EP loss probability. However, the benefit of additional servers can be observed only as far as their aggregate transmission capacity is small. When the transmission capacity is large enough, the system constrained by the energy production system. In order to further increase the system service capacity, a more powerful energy production system is needed. Dimensioning UABPS. An EP and DP range models. In order to properly model the size of the PV panel which is installed on each UABPS, we considered the hourly fluctuation of the energy production and of data traffic. Hence, the EP and DP range are not constrained but time dependent and denoted by BT, beta T, and lambda T respectively. To model the hour variation of the rate, we started from real PV panel energy production data, and we take the data provided PV watt. The data estimates the electricity production of the typical poly or monocrystalline silicon PV panel systems, taking into consideration realistic solar irradiation patterns corresponding to the typical meteorological year in the considered area, with a gradually of the hour. The main typical losses occurring in the real PV panel system during the process of solar radiation conversion into electricity are accounted for 14%. The efficiency achieves 20%, 28%, which means that about 5 square meters can be assumed per each kilowatt per of PV panel capacity, 29, while its weight 2.55 kg per square meter for off-the-shelf portable PV panels. The elevation at which the PV panel operates, if it is installed on an UABPS, makes it more efficient, since it is working at lower temperature, and this increases the energy production between 7% and 12%, as reported in 13. For this reason, the data of energy production provided by PV watts are increased by 7%. We normalized hourly energy generation during the year, so the generated energy in each hours is given as a function of the yearly peak hour production. Then the meteorological winter and then summer periods are selected using the normalized energy production from 1st December to 28th February and from 1st June to 13th August respectively. The average hourly energy production during the day computed, which provides the shape of the hour EP arrival rate during the typical day in the winter and summer seasons, which are reported in Figure 5 in blue and orange respectively. Thus, the hour EP arrival rate in EPs derived as beta T, B, F, and E, T, where F and E, T is the energy production shape as previously derived, and beta B in EPs. In the factor is a factor which defines the arrival rate of EPs. To formalize the variation of the traffic demand, we use the traffic data provided by a large Italian mobile network operator, which reported the traffic demand volume in a wide area around Milan, in Italy, for duration of 2 months in 2015, with gradually of 15 minutes. Data are aggregated to have an hourly granularity, and the average hourly traffic demand during the day is computed. Then data are normalized and the daily pattern FNDT is figure LEP on the left, LEP BG in the middle, LEP MT on the right, versus lambda with a different number of servers. Vertical lines represent stability conditions. Dashes horizontal lines reported EP loss probability given by the Erlang formula in 4. Normalized pattern for the hourly traffic demand in black and for the hourly energy production in winter in blue and summer in orange. Obtained. It is reported in figure 5. The parameter lambda t in DPs is computed as follows, where L in DPs is the factor which scales the amplitude traffic rate. Model of the PV panel. We now derive the size of the PV panel which has to be installed on each UAVBS makes a system stable, i.e. to serve the traffic. The parameter B in EPs is defined as B EPJ CPV RP, where CPV is the capacity of the PV panel in watt. EPJ is energy carried by an EP in JEP, and R peak is the ratio between the yearly maximum power production per hour of the considered PV panel and its normal capacity, and it varies according to the location of the PV panel. Substituting 9 in 1, the system results stable if the following conditions hold: mu minus lambda t the mu, R peak FNET EPJ per CPV. Parameter setting. In this part of the work, we consider a LTE MU-MIMO UAVBS equipped with a single MIMO antenna, which supported the ground LAN, providing additional capacity to users. We assume that its bit rate BR is a weighted average of the access and BH bit rate, BRA and BRBH. Summary of the PV panel capacity, surface, and weight. Computed as BRA, TA, BRBH, TBH, TABH, where TA and TBH are the time needed to transmit a DP in the access and BH networks, respectively. BRA and BRBH taken from 20 are 16.9 bit and then 72 bit per second, respectively. YTA and TBH are respectively equal to the 3.35 10 per 4 minus 4 second and then 0.79 10 for 4 second, assuming that the size of the each DP is 709 bytes as 31. From these parameters, we derive that BR is 27.39 bits and mu 4.28 dp millisecond. The size of the each DP EP, which is the necessary amount of energy needed to transmit DP, is the average between the energy needed for the transmission of the DP in the access and each in the BH networks. To compute these values, the models employed 3233 are used, which depends on the hardware components of the antenna, as well as on the transmitted power, which varies with the elevation of the drones. Here we assume two different elevations set equal to 70 meters and 120 meters, since the maximum allowed drone elevation until 31 December 2020 in Italy in 70 meters, but from 1st January 2021, considered drones are allowed to fly up to 120 meters, according to the European regulation reported in 34, given the power consumption of the access and the BH interface, PA and PBH, respectively, taken from 33 and reported in Table 2 at the two considered elevations. The size of each EPJ in joule is EPJ equal 0.5 PA per TA, PBH PH TBH, where TA and TBH denoted the time needed to transmit a DP in the XS and BH network, respectively. Because of the difference of the PA and PBH and the two different elevations, the DP size larger in the drones at 120 meters than when it operated 70 meters. See Table 2. Since more power is transmitted to reach the users. Finally, from Solar's production data provided by the 27, we know that the yearly maximum power production of the PV panels installed in Turin is equal to 76% of its normal capacity, and the RP is set accordingly. Performance evaluation. Through the stability of the system, we investigate the capability of the UAVBS to serve the traffic demand and the relation between traffic and energy production. We focus on daylight time, i.e. from 8 to 17 on the x-axis of the figure 6 parameter band B, which determines the energy production as in 7, varies from 0.1 to 10.0. As previous mentioned, the normal capacity of the PV panel corresponding to a value of B depends on the elevation at which UAVBS operating. When B is 0.1, the normal capacity of the PV panel is 0.79 watt and 0.787 watt if it is 70 and 120, respectively, corresponding to the surface of 0.410 minus 2 square meter square, and the weight are no longer than 0.1 kilogram, with B equal to 10.0. The nominal capacities are 78.95 watt and then 83.27 watt, which means a PV panel surface of the 0.4 meter square, with a weight around 1 kilogram. For the considered elevation, the capacity surface and the weight for different values of B in the considered interval are reported in Table 3. The table indicates that the considered PV panels are small enough in terms of both surface and weight to make their installation feasible on UAVBS. The green and red bars figure 6 indicate the values of B, which makes the system stable and unstable during each hour reported on the y-axis. When the system is unstable, the energy is not enough to serve all traffic demand. Results are given for two different values of traffic, represented by the L equal to 0.16 and 1.17 in figures 6b and 6d. In summer and winter, the figure shows that as expected, the low traffic demand can always be satisfied even in winter and with limited energy production, while high traffic demands are satisfied only in summer, when the energy production is high and large PV panels are considered. Larger values of the B are needed to serve the traffic during low energy production hours, from 8 to 10 and from 14 to 16, then during the peak energy production period, from 11 to 13. The probability to the loss EP's LEP is plotted in figure 7, where each curve corresponding to the given hours of the day. Different values of the B are considered from 0.1 in value to 10.0. In red, LEP grows when low energy production levels are needed. That is, when traffic is low, production is high. Indeed, the peak of the LEP always occurs 12. In particular, 12 in summer, beta equal to 0.50 and then 2.85 stabilizes the system when L is 0.16 and 1.72 respectively, maintaining LEP no longer than 0.02, 0.32 as 16 values of B larger than 0.45 and 7.6 are needed. This means that in the summer in summer during peak hours production. If the UAV-BS operates at 120 meters of altitude, it needs PV panels with a capacity of 1.2 and 24 watt. While it is at 70 meters, the capacity slightly decreases to 1.1 watt and then 22.5 watt. For both the elevation, these nominal capacities correspond to a panel surface of 0.610 square meter square and then 0.12 meter square. If L is 0.60 and 1.72 respectively, in case UAV-BS provides a service out of peak of the energy production, the needed PV panel's capacity at 112 meters increase up to 3.7 watt and then 63 watt, corresponding to PV panels areas no longer than 0.02 meter square and then 0.3 meter square. In case of UAV-BS operation at 70 meters, the indeed nominal capacities are 3.55 watt and 60 watt, without significant reductions of PV panel surfaces. In winter, the situation is similar as illustrated in figures 6C, 6D, 7C, 7D, even if larger values of BIP than in summer are needed and the lower values of LEP are reached. Because of the lower energy production which characterizes the season, as shown in figure 5 at 8 and 16, when L is 0.16, B greater than 4.2 and 3.35 respectively, is needed in order to stabilize the system, keeping LEP lower than 0.03. This means that with the traffic intensity, a PV panel whose nominal capacity between 28 watt and 35 watt is needed if UAV-BS located in 120 meters, which is a surface between 1.70 meters and 1.40 meters squares. This capacity rises between 26.4 watt and 33 watt, with no significant variation of the needed PV panels area. If the UAV-BS elevation is 70 meters, at 12 B equal to 0.4 is sufficient to make the system stable, provided by the PV panel with the normal capacity of 3.3 watt, surface equal to 0.17 10-1 meter square. In this case, LEP is 0.03, increasing L up to 1.72. For example, increasing the traffic intensity only during the peak hour production from 10 to 14 be larger than 7.05 makes the system stable, with the LEP no longer than 0.32, which is achieved when the installed PV panel's capacity is 71 watt, which has a surface of the 0.3 meter square. Separately considering winter and summer, figure 8A and 8B provides the percentage of the time during a day for which the system is stable, increasing the value of the L, and hence the traffic from 0.1 to 3.5. Each curves in the figures correspond to different values of B, from 0.1 in value to 10.0 in red. These figures confirm that large values of the L requires large values of the B to achieve the stability of the system. In winter, the system is stable 100% of the time, meaning it can serve all the traffic at each time of the day. Only if traffic is low, L is between 0.1 and 0.22, and the production system is large, B larger than 7.8. The nominal capacity of the PV panel that is needed is at least 61.58 watt if the UAV-BS is located at 70 meters, while it is listed 64.95 watt when it works 120 above the ground. If lower values of the beta B are used, the system reaches stability less than 80% of the considered time and with be lower than 1, which corresponds to nominal capacity smaller than 9 watt. 9 watt. For both considered elaboration, stability occurs for more than half of the time. In summer, the situation is better and the system is stable for the whole considered time even under high traffic air up to 1.29 if B is larger than 9.95. The system results stable for more than 80% of the time. When L is 0.43, if B is between 2.0 and 10, i.e. if the normal capacity of the PV panel 50.8 watt, if the drone H is 70 and 16.7 watt, if the UABBS located at 120 above the ground, but for less than 60% if B is lower than 1.45, which is a scenario where PV panel reach nominal capacity of 12 watt is employed. As discussed above, large values of B and small values of L, besides making the system stable, generates large values of energy losses LEP as shown in figure AC and AD. LEP decreases with B and L until the region where the system is unstable, where LEP assumes a constant value, which is up to 0.54 in summer and up to 0.27 in winter according to the B and L setting. These results show how the models proposed in the previous section can be used to understand the relation between traffic demand and power supply and dimension the UABBS power supply system. Results also highlight the importance of the evaluation of the period of the day and of the year in order to verify the feasibility of the solution and the proper sizing. Conclusion: the use of UABs on which BS equipped is mounted is a promising solution to dynamically provide additional capacity and length. Usually these UABs are powered by onboard batteries, which makes their survival short because of the scarceness of the energy availability. For this reason, solar-powered UABs are interesting alternative which however raises a number of challenges related to dimensioning and the intermittent nature of energy generation. In this paper, we model a PV panel-powered LTE-MU-MIMO UABs and investigate the different system operating regions. As a function of traffic demand and energy production, our result revealed that the usage of the PV panels as a unique energy source for the communication unit of the UABs is an efficient solution, but it has to be proper sized in order to operate in stability conditions.